A 43-kilogram child at a playground pushes on a 5-meter diameter, 185-kilogram merry-go-round until it is spinning at 12 RPM. She then runs tangent to the merry-go-round at 4.6 meters per second in the same direction it is spinning, and she jumps onto the outer edge. What is the angular velocity of the merry-go-round just after the child jumps on? So I'm going to draw a picture. This is a bird's eye view. I'm looking down at the merry-go-round. Okay, first the merry-go-round is pushed. It doesn't matter who pushes it. It has an initial angular velocity. So this is the initial angular velocity of the merry-go-round. Okay, is 12 RPM. We can change the units to SI units later. And the girl, runs tangent to the merry-go-round. So this is her initial velocity, the velocity of the girl initially. Okay, is 4.6 meters per second. She's running in the same direction. So let's say this is her over here, and she's running this way. Now compared to the merry-go-round, she's quite small. We're going to treat her like she's a particle. And she jumps onto the merry-go-round. She's running tangent to it. So do you see how like her direction, her velocity, is tangent to the actual circle, the merry-go-round? She jumps on it. When she jumps on it, she's helping it rotate even faster, right? Because she's jumping on, it's like she's pushing it and making it go faster. Okay, so this is like an inelastic collision, and it is angular because there's a rotation happening. So there's no other external forces that are acting on the system that's making the merry-go-round rotate. So that means there's no external torque. So since there's no external torque, we can say that the moment of inertia, the angular momentum of the whole system initially equals the angular momentum of the whole system final. So before she jumps on, the angular momentum is equal to the angular momentum after she jumps on. Okay, so what's the angular momentum before she jumps on? We have the angular momentum of the girl plus the angular momentum of the merry-go-round is equal to the angular momentum of the girl after she jumps on plus that of the merry-go-round after. Okay, so we're treating the girl like it's a particle. Okay, the girl is a particle because she's a lot smaller than the merry-go-round itself. She doesn't have like a certain mass, she doesn't have a certain like volume that we're worrying about, okay? The merry-go-round, it tells us, is 5 meters in diameter. So from the axis of rotation to the girl itself, that would be our R vector, and that's the 2.5 meters because it's half of the diameter. Okay, so what are the formulas to find the angular momentum? So we have angular momentum is equal to, just like we originally had linear momentum is mass times velocity, angular momentum is moment of inertia times angular velocity. Now, if we're talking about a rigid body, then that's the formula we would use. We would use the table to find the moment of inertia depending on the shape of this object. Now we're talking about a girl. There's another formula for angular momentum for a particle. Okay, and that's because the moment of inertia of a particle is mr squared. So time it by omega, and now we have the angular momentum of a particle. Okay, omega also is equal to v over r, because we have that formula v equals omega r. So if we replace omega with v over r, now we have this equation, mrv. Right? And this equation is true as long as the particle is moving perpendicular to that r vector. So the particle, in this case it's the girl, is moving this way. This is her velocity vector, and the r vector is in this direction. The angle between those two vectors is 90 degrees. So because the angle between those two vectors is 90 degrees, we don't really need to worry about this sine beta that comes into the equation, because sine of 90 is 1. So all of this goes away. So it doesn't matter which equation we use for the angular momentum of a particle if we know that the angle between the velocity vector and the r vector is 90 degrees. So we can use mr squared omega or mrv. They're both the same thing. And it's the same as I times omega, because I is mr squared for a particle. Okay, so I hope this is making sense. So for the angular momentum of the girl, we're going to say it's, well, what do we know about the girl initially? Do we know her omega or do we know her v? Well, she is running with a velocity of 4.6, so we know her v. So I'm going to write mass of the girl, r, times v of the girl, initial. So I'm using mrv because we know v, plus the angular momentum of the merry-go-round. So for the angular momentum of the merry-go-round, I'm using this I times omega equation. Okay, so this is the original angular velocity of the merry-go-round equals, so now I have the angular momentum of both of them. Now the girl is now on top of the merry-go-round, so I'm going to write it as the moment of inertia of the girl plus the moment of inertia of the merry-go-round times omega final. Okay, so this is similar to when we did linear momentum. We'd say m1 v1 plus m2 v2 equals m1 plus m2 v final. We did this when we knew that we had an inelastic collision. Well, this is an inelastic collision because the girl jumps on the merry-go-round and now they're stuck together. She's staying on top of the merry-go-round as it spins, so they're spinning together. Now instead of m1 v1, we're using this formula. I1 omega 1 plus I2 omega 2 equals I1 plus I2 omega final. So it's the same thing as what we did in a linear fashion. Now the I1 for the girl is mr squared. And for the merry-go-round, we have to look at the table. Now the merry-go-round, we're going to treat it as a disk. Moment of inertia of a disk is 1/2 mr squared. Okay, and then the I1 and the I2 is the same thing. So we're just putting both of those moment of inertia equations back into that. Okay, because for the girl, we don't know her omega 1, so the angular velocity of the girl, because she's running in a straight line, we know her linear velocity. So we needed to convert omega into v over r, and that's where this equation comes from. Okay, so I hope you can see this is very similar to the linear momentum. When you have an inelastic collision, it's all set up the same way. The confusing thing is that for angular momentum, there are different options when it comes to which formula to use. Okay, if the velocity vector of a particle and the r vector are perpendicular, it doesn't matter which formula you use. You can use I omega. The I of a particle is mr squared, so then you have mr squared omega. And if you don't know the omega because it's a girl that's running in a straight line, then you change the omega to v over r and you end up with mrv. The sine beta goes to 1 because beta is 90 degrees. And now all those equations are the same. Okay, so I'm going to clean this up. So let's start to plug in what we know. So I'm just going to simplify these r's actually. I mean these I values first. Okay, so I have mass of the girl, r, the radius, velocity of the girl initially, plus I, so this is the moment of inertia of the merry-go-round, which is a disk, 1/2 mr squared. If you look at the table, it will tell you the moment of inertia of a disk that rotates about its center is 1/2 mr squared, times omega, the angular velocity of the merry-go-round initially, is equal to the moment of inertia of the girl plus that of the merry-go-round. Okay, so the moment of the inertia of the girl, we're treating her just as a particle, mr squared, plus of the merry-go-round, it's a disk, 1/2 mr squared. This is the girl, this is the disk, times omega final. And the omega final is what we're looking for. So we can rearrange and solve for omega final. Okay, and now we can start to plug everything in. So the mass of the girl is 43 kilograms. The r was at 2.5 meters. The velocity of the girl initially was 4.6 meters per second, plus 1/2 the mass of the merry-go-round now, so it's 185 kilograms. The r, the radius of the merry-go-round, is still 2.5. The angular velocity of the merry-go-round, so it was spinning at 12 RPM. We just need to figure out what that is in radians per second. So we have 12 revolutions per minute. We want to get rid of revolutions, so we'll put it on the denominator so it cancels out. We want radians instead. 1 revolution is 2 pi radians. And then we also want to get rid of minutes, so we'll put it on top so it will cancel out. Instead we want seconds. 1 minute is 60 seconds. So I'll just type everything in. And I get 2 pi over 5. Okay, you can put it in as a decimal if you like as well. So now I have 1/2 mass of the merry-go-round, r squared, and then omega of the merry-go-round, which is 2 pi over 5, over mass of the girl is 43. The r is still 2.5 squared plus 1/2 mass of the, I wrote D for disc, but I'm going to change that to merry-go-round. So that's 185. R is 2.5 squared. All right, I'm going to type all of this up. And I get 1.44 radians per second. All right, let's take a look at our significant digits. So I have 3 significant digits up above here. I have 3 over here, 3 over here, 3 over here. So my answer should have 3. So I'm all good. All right, I hope that helped. Thanks for watching.